All right, so in the previous lecture we introduced the Cauchy stress tensor. And then what I mentioned last time is that as with other fields that we have introduced before, there's fields that are more associated with the deformed configuration, there's fields that are more associated with the deformed configuration. So if you think again of your body in the reference configuration and your deformed body, the Cauchy stress is associated with the deformed configuration because it basically measures force per deformed area, right, for planes defined by normal n in the deformed configuration. But you can imagine that we can always start mapping things back to the reference configuration. So the other stress tensor that you might find is P. So this is it's also stress, but it's going to be sort of bringing back the sigma stress tensor. So, and like we did for the velocity fields, what this involves is usually some multiplication with f. So f is what allows you to move from one to the other. So P is the first Euler-Kirchhoff stress tensor. First Euler-Kirchhoff stress tensor. And you can think of this as sort of force per reference area. So this is sort of force per reference area, whereas the Cauchy stress tensor is force per deformed area or real area. If you bring back this looks like Nanson's formula, JF minus transpose. So the first Euler-Kirchhoff is force per reference area. Now one of the things that you should note is that P is not symmetric. And because of that, it's really not, even though it's sort of a natural way of bringing back the calculation of the stress. So it's still force, but now with respect to the original area. Because it's not symmetric, it's usually not that nice to work with numerically. And instead, a different stress tensor is introduced, which is the second Euler-Kirchhoff stress tensor. Kirchhoff, and it has 2H and 2F. And that one is related also to the to sigma, or you can relate it to P. It's just one extra F inverse. And this one doesn't really have a nice physical interpretation because this is sort of kind of a reference force per reference area, but this term of reference force doesn't really make that much sense. So it's sort of like pulling back, if you have like a traction here, if you multiply by F inverse, you're going to get the corresponding traction in the reference, but it's not really a force, so it doesn't really have a physical interpretation. But the nice thing about this is that it is a symmetric stress tensor. And because of that, it's actually quite commonly used. So both P and S are associated with the reference. As I said, P is sort of force per reference area, and S is sort of, the second Euler-Kirchhoff stress is sort of a reference force per reference area. But this concept of reference force doesn't really have a real physical interpretation. And that's about it. Those are the three most common ones. You'll sometimes see this tau, which is the Kirchhoff stress tensor, which is almost the same, just without the volume change. So this is the Kirchhoff stress tensor. Tau, and it's basically almost the same relationship between it's related to sigma, basically just scaled by the Jacobian. That's it. And that's about it. So those are the most common stress tensors. They all measure stress. They all measure some sort of force per area. And the reason why they are not the same is because you are sort of switching this area for a reference area and switching force for like a reference force, even though that doesn't have a real physical meaning. That's about it. The ones that will come up a lot in the future are obviously the Cauchy stress. The second Euler Kirchhoff appears actually quite a bit. Actually, all four of them they will make appearances. Some in some cases there are other options, but these are really the most common.